So this is the main memory. Let us consider a main memory which is of 2 power 5 locations. So there are 5 bits for each memory location starting from 00000 to 11111. So now we have a cache. Let us say we have a small cache. A cache is containing 8 lines or 8 blocks of data. So which means it can be addressed with just 3 bits. Now, obviously, we cannot have a cache which is of size 2 power 5 locations because then it will just be a replication of the main memory and we do not have so much space on the processor. So basically, the cache is going to be of small size as compared to main memory. That's the first point. So which means that not all data in the main memory can be put in the cache. So only some of them will be put in the cache. Now we have to have a way of mapping the data of a certain location in the memory with a certain location in the cache. It cannot be random. It cannot be just you just pick some location and put it somewhere in the cache. It can't be that way. It has to be a proper organized way of address mapping between the memory and the cache. So this is the whole concept based on which different cache architectures have been designed. So now the first one we'll look at is direct mapped cache. So how do we map a data? Now let us say we have address 00000. One of the ways of mapping is the first address will go in the first location, which is 000. The second one, which is 001, is going to go into 001 and so on. So basically you're going to get to 8 locations, which is basically 1000. So this is all binary. This is not hexadecimal. So this is literally 5 bits of memory. So you have 01000 and that's going to go, or rather it is 00111. So that is the 8th location in the main memory and that will go into 111. So let us assume we do a mapping like this. So then what will happen to the next location, which is 01000? Where would you put that? You would have to come back and put it in the first place. So 01000 will go in the first place, 01001 in the next one, and so on. So basically, you can write this as the address modulo 8. So that will be the location in this cache. In other words, there is a better way of conveying the same information. The way we do that is, so let us pick the memory location. So let us, for example, pick 00001. This is the 5-bit memory location. Now you want to put this into a cache which has 8 locations, which means you need 3 bits to address. So what we do is we pick the least 3 bits, okay, the least 3 bits of the memory location, and that is called as the index. Like I said, there are going to be several terminologies in the cache, so you have to be aware of it. So we call this the index. So we will pick the content of 00001 and place it in 001. So like it is, like they have shaded it here, the gray color content is 00001. You place it in 001. So how do you get 001? You look at the 3 least significant bits and you place it there. Now the problem will be, what will you do with these locations? Because these locations also have the same index. So index, you can think of it as this. The indexing into the cache is basically this index. So there are going to be a lot of other addresses which will also map to the same index. So like you can see here, the other ones which they have colored here, 01001, 10001, 11001, they are all going to map to the same index into the cache. Basically the same row in the cache. So how will you deal with it? You will have to have some way of distinguishing, okay, this is the data present in this address versus the data present in this address. So how will you distinguish? So for example, let us say we have AB as a content here and CD as the content here. I might still be mapping to the same location, but when I want the data from 00001, I want to be reading AB and I don't want to be reading CD. And when I give this location 10001 from the processor to the cache, I'm expecting to read CD and I don't want to be reading AB. So there has to be some other way of denoting that this is the data that is present. So what we do is, like I said, 00001 versus let's say 10001. So first thing, we pick the index. So this is an 8-line cache, therefore 3 bits for the index, for the cache index. So this is the 3-bit index. So we are sure that both of this data, the content of both of these addresses are going to go into the line 001 of the cache. But what I'll do is, in addition uh, to storing the data here, so I'm just, this is shown in a horizontal way. I've just written it here in a vertical way. So this is 000, this is 001, 010, and so on. So I'm going to pick the content of this address, which is the data. Let us say the data is AB. I'm going to put that data in the cache. Where will I put it? I will put it in index 001 because that is the index of that address. In addition to storing the data, I'm also going to store these other 2 bits of the address. This is called the tag. Now this tag is going to be unique. So if I have the other 2 addresses, I still have the same index, but the tag is going to be different. So this way you can uniquely identify the data. So what I'll do is I'll store the tag along with the data. Now, how do I know what is a tag? Tag is basically the other leftover bits from the address. So now let us do it from the beginning. The processor is going to send the address 00001. So you're going to look up in the cache. The cache is initially empty. So you will bring this content or the data from the memory and put it in the cache. Now, where will you put it in the cache? You will find out what is the index. You will place it in that index. You will fetch the data from memory, put it in the cache. And in addition to that, you will place the tag in the cache. Now, second time, let's say, I'm going to get this address. So now the data is in the cache. Now let's say the second time the processor sends this address. So what I'll do, I'll split this up into tag and index. So this is the tag, this is the index. I will go to the index 001. I will try to match the tag. So the tag from the address versus the tag present in the cache. I'll do what is called a tag match. When the tag matches between the address the processor sends and the data and the tag present in the cache, it means that the data is present in the cache. And when the data is present in the cache, it is called a hit. So in addition to this, like I mentioned, initially the cache is going to be empty, right? So initially, let's say the cache is empty. So there's going to be no tag here to do a tag match. There's basically nothing there in the cache. So there is no point doing a tag match because there is nothing there. So what we usually do is we put what is called a valid bit. Okay, so how the valid bit looks like is just 1 bit, 1 or 0. So initially when the cache starts off, all the valid bits are 0, the data is empty, the tag is empty, basically everything is empty and the valid bit is 0. So what you do is when you get an address, let's say 0100, you split it up into tag and index. And then you go to this index and look up for the valid bit. So if the valid bit is 0, it means there is no valid data there. So there is no point doing a tag match. So basically it means the cache is empty and therefore it is a miss. So now you go to the memory, bring the data, put it here. you update the tag and make the valid bit 1. So now this means the data is valid. Okay, so this is another important terminology here. So what we have learned so far, we have a valid bit in the cache, which is 1 bit. We have a tag and we have the data. And we have a concept called index, which is used to index into the cache. Now, there is a concept called a block. So far we have ignored what is the width of this data. So we have just said we bring in some 1, 2, and 5, 6, and so on. But if you remember, we have this concept of a byte addressable memory, and uh, each memory is going to contain, each memory location is going to contain 1 byte of data, which means if we are bringing 4 bytes of data, we need to read 4 consecutive locations to make it 32 bits of data. So we'll now look at what is the concept of a. So when you read in data, if you want to read a load word, if you have an instruction load word, you want to read in 32 bits of data. Let's say if you're talking of a MIPS processor, a word is 32 bits, and therefore you want to read 4 consecutive memory locations. And therefore, this 4 consecutive memory locations is called a block, or 4 bytes of data. So how does a cache look like? So instead of dividing the memory into bytes, what we do is we divide it into blocks. So when you read a line, this line is going to contain all 32 bits of data, which means it's going to contain an entire block. Okay, so basically the address that you send to the memory to read the data is basically a block address and not a byte address. So which means it is again going to be multiples of 4. So you will send 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, and so on. So that is, and the entire block, that is 4 bytes of data, is going to be read in and placed in the cache. Okay. So now let us see this example. Maybe you can stop at this point and see how it works. So we have a cache which is of size 8 lines, as shown here, 0 to 7. It's going to have 32 bits of data. It's going to have some tag bits. It's going to have 1 valid bit. Now I'm giving you a 32-bit address. You have to find out how many bits is the index, how many bits is the index, and what is the index, and what is the tag, and where are you going to place the data. So which line of this cache are you going to place it here, are you going to place it here, here, etc. Now let me describe how we are going to do byte access in a cache. Now I just described previously that we fetch an entire block, which means we fetch 4 bytes of data. Now, what if I issue an instruction such as load byte, which means I want to read just 1 byte of data into the processor. So what we are going to do is we are still going to load an entire word into the cache, because let's say we previously did a load word and then we are doing a load byte. So we issue a load word, we fetch the entire word. So I have fetched the entire 32 bits. So 4242, 4242 is the data in hexadecimal. So this is basically, I hope you understand, this is hexadecimal. So 01000010, that is 42. That is the first byte. This is the second byte, third byte, and fourth byte. I've placed all of that in this cache and I have the tag bits and everything. So now let us say the next instruction is load byte and I want to read the first byte. So how do I do this? So basically, in order to do this, what we will do is we are going to introduce another terminology. So if the cache is going to allow this byte access, then we have to split this address differently. So in addition to index and tag, we have to allow what is called a byte offset. Okay. So what is this byte offset? Like we know, we have already seen with MIPS that our PC is always going to be multiples of 4, which means the LSB 2 bits are always going to be 00, right? We have seen that before. So what we will do is we will use the same concept here. We will leave the least 2 bits of the address, because if they are multiples of 4, they are always going to be 00. And we will start the indexing after these 2 bits. So basically, you leave the 2 least significant bits because we expect them to be 00. And then we start the next 3 bits will be index. Why is it 3 bits? Because we have 8 lines in the cache, and therefore it is 3 bits for index, and the rest of it will be tag. Okay. So now the advantage with this kind of a system is, let's say I get a load byte, which means I'm going to get some address which is something like this, which is not a multiple of 4. It will not be multiple of 4 because I want to read this byte. So now what you can do is split this up. So this is what is called the byte offset. It's also called sometimes block offset. Let us call it byte offset. This is the index. The rest is tag. So what I'll do is, the procedure is same. Go to this index, which is 010, that is this line. Check for the valid bit, it is 1. Do a tag match, right? I repeat, split this address into tag, index, and byte offset. Go to that particular index, which is 010. Check if the valid bit is 1. Yes, the valid bit is 1. Check if there's a tag match. If there is a tag match, which means the data is present, and I only want the data present in the 0, 1 offset. So basically they're going to be 0001, 1011, because there are 4 bytes in that block. So how you're going to read that offset is, this is the first offset 0, this is the second offset 1, this is the third offset 2, fourth offset 3. So if you get an address with 0, 1 as the byte offset, you're going to pick this data. So maybe I should write some unique number here so that you will understand it better. Maybe it's 4, 2, 1, 2, 3, 4, 5, 6. Let us say this is the data. If I get a byte offset of 0, 1, I'm going to pick 1, 2 as the data. So it's always from left to right. If I get 1, 0 as the byte offset, I'm going to pick this one. If I get 1, 1, I'm going to pick 5, 6. If I get 0, 0, I'm going to pick the first byte.